My talk focused on describing the science and technology of a unique multifunctional material in thin film form that we call ultra nanocrystalline diamond, or UNCD for short. And we are developing for a new generation of industrial high-tech implantable medical devices and prostheses. I am at the University of Texas, Dallas, but also I have three companies: Advanced Diamond Technologies, 2003, sold to 2019 to a large company, and now Original Biomedical Implant, OBI USA, and OBI Mexico. So I have the work we did in discovering UNCD was with Dr. Dieter Gruen and Alan Krauss in Argonne National Laboratory in the 90s. And then with John Carlyle, I started the first company. And then I have students and postdoctorate from all over the world, and a lot of interaction with people from Latin America, since I am originally from Argentina, and particularly from Mexico now, where I am doing a lot of work, and I'm going to explain why. So I will review first the R&D on growth of microcrystalline diamond and nanocrystalline diamond that started in Europe. Then I will present a review of the R&D on growth of this transformational, multifunctional, low-cost ultra nanocrystalline diamond coating. And low cost is very important because otherwise we cannot put it in the market. And then I will review the technology development for a new generation of UNCD coated-based industrial products, high-tech and implantable medical devices and prostheses, and present the future. So, the material science. For many years, European scientists started growing diamond films, polycrystalline diamond film, using a mixture of 1% methane, 99% hydrogen, flow into a vacuum system, capping microwave power, and producing the diamond films. But that needed a high activation energy of 20, 30 kilocalories per mole, because they have to get the hydrogen out of the carbon CH3, C2, CH2, and that took heating the substrate to 600, 800 degrees. And the reason they put so much hydrogen is because they observed a graphitic phase being co-deposited, and atomic hydrogen produced in the plasma each graphitic phase easier than diamond. But what they didn't realize is that a small nanocrystalline diamond that we're trying to renucleate were also etched by that. And in the end, they were also only to grow microcrystalline diamond due to the coalescence of the nanograins that they couldn't survive. And then when they were able to switch to 4% methane, 96% hydrogen, they were able to grow what they call nanocrystalline diamonds, grain size of 10 to 100 nanometers. But when we started looking at that, we saw low nucleation density of 10 to the 4 to 10 to the 8, columnar growth, large grain size in the case of 1.5 microns, and high surface roughness. And we wanted to have a material with much smaller grain size and a smaller surface roughness. So that's why we started looking at an alternative and having a source of carbon without hydrogen. And that's why in the 90s, three scientists discovered the so-called C60 fullerene molecule. And they got the Nobel Prize for that, obviously. It's a unique molecule. And since I am originally from Argentina, I like everything with a football shape. And so the carbon atoms are all there in the corners of this football-shaped structure. We bought 10 grams of C60 fullerene in 1990, and that was $5,000. We put it in an oven, heated to 900 degrees, brought the C60 into the gas phase, flew argon into the vacuum system, and we saw this green plasma. We didn't know initially what the green was coming from. But when we did the TEM analysis of the film, we saw that the grain size of our polycrystalline diamond films were 2 to 5 nanometers, which still are the smallest grain size of any polycrystalline diamond film in the world. And that's why we coined the name UNCD, ultra nanocrystalline diamond, or UNCD for short. However, I was very interested in bringing this to the market, and very expensive if we're going to have to buy 10 grams of C60 fullerene molecule for $5,000. Complicated, a dirty oven creating a lot of soot connected to a high clean vacuum system, not good. And we didn't see how we were going to be able to scale up the process to grow the UNCD on large areas to do the low-cost UNCD growth needed for bringing it into the market. So then we decided to do more fundamental and applied science, computer simulations, experiments, and we found that if we replace the hydrogen 99% by argon 99%, we were able to grow the same film. Now, everybody growing these films do what is called the seeding process, where you put the substrate in a ultrasonicator now mainly, with a solution of nanocrystalline diamond particles in methanol. The sound waves shake the particles embedded on the surface, and those are the so-called seeds, simulating the seeds that you put in the ground. What we found is that in the plasma, the green plasma we produce, the CH4 is cracked into C2H2 and argon colliding there, develop these C2 dimers that are two carbon atoms, but without hydrogen. And that's why the low activation energy in our growth film is 6 kilocalories per mole, high renucleation rate of 10 to the 12 per centimeter square. And because of this unique patented process, we are the only ones that can grow these diamond films at 350 to 400 degrees centigrade, as shown here on the right. Then we did in situ optical emission spectroscopy and found that the green light from the plasma was coming from emission from these C2 dimers. Later on, we decided to do more fundamental science and explore what would happen if we put nitrogen in the gas phase as argon CH4 nitrogen here on the top. The color of the plasma is more violet like white. And what we found is that we grew the film with 10 nanometer grains, 1 to 2 nanometer grain boundary, and this is the first diamond film that is electrically conductive in the world. Nitrogen atoms get into the grain boundary, link to dangling bonds of carbon atom in the grain boundaries and provide the electron for conduction. So we were very interested in continuing the characterization of these films, and no matter where we grow it at 800 degrees or 400 degrees, the grain size are in the range of 2 to 5 nanometers, as shown here at the bottom. Now, when we were doing a UV Raman spectroscopy, and when you do Raman spectroscopy of a gem of diamond, the characteristic peak is this one at 1332 centimeter minus 1. We were seeing that peak, but also we were seeing this broad peak that correspond to sp2 carbon bonding. And so people started saying, well, you also have graphitic impurity. And we said, those are bonds of carbon in the grain boundary. So we have to synchrotron at Berkeley laboratories doing NEXAF, near X-ray absorption factor spectroscopy. And when you do NEXAF on from Europe, and then our UNCD. And when you do NEXAF on graphite, you see the pi peak here. So this shows clearly that we didn't have a graphitic impurity phase in our UNCD and was coming from the dangling bonds of carbon in the grain boundaries. So no matter how thick we grow the films, up to 2 microns in this example, the surface roughness is in the 2 to 5 nanometers, and our films exhibit the lowest coefficient of friction comparing with diamond-like carbon or microcrystalline diamond. And that is very important for some of the applications we have developed for products. Now, I am very interested in continue reducing the cost, and the seeding process takes 1 hour, which contribute to the cost. So what we developed in the last 5 years is a process that we call bias-enhanced nucleation, bias-enhanced growth. So if we put semiconductors or metallic substrates and we apply a negative voltage with respect to a positive electrode on the top, we can accelerate the carbon plus, argon plus, CHX plus ions that implant on the surface and nucleate the film. And with this process, we can grow exactly the same UNCD films as we were growing with the seeding process. Here we see the high resolution TM on the top, and at the bottom, the Nexus to confirm that our UNCD doesn't have the graphitic phase. So with nitrogen in the grain boundaries, we have semi-metallic conductivity, and this is not doping. Nitrogen cannot replace carbon atom in the diamond because it's too deep, 175 eV. So the nitrogen gets into the grain boundary, attached to carbon bonds, and provides electron. On the other hand, we demonstrated that with boron, we can do true doping, where boron can replace carbon atoms and provide electrons to the conduction band, and with that, we have very good metallic UNCD films. The hardness and the Young modulus are very close to the hardness and the Young modulus of the gem of diamond, the strongest material we have on Earth. Low friction, and from the biological point of view, we demonstrated in the last 15 years that UNCD is the best biocompatible coating to put in the human body because it's made of carbon atoms only. And we humans are made of carbon atoms, is in our DNAs, proteins, molecules, and everything else. So we can grow it at very low temperature. We are developing MEMS structures as well. And let me show you. On the left, you can see the large area industrial MPCVD system from E+, a company in Germany, close to Cologne. I've been working with this company, with Ralph Spitzel, the creator of the company, for many years, and this was the last device he developed that is an industrial that allow us to grow extremely uniform UNCD film on up to 200 millimeter wafer. On the other hand, we also produce UNCD by hot filament CVD, where we heat an array of hot filaments, tungsten up to 2300 C, and the CH4 crack on the hot surface, producing the carbon to create the film. And initially, when we started our advanced diamond technology, we didn't have this large area E+ system, so we had to go with a large area commercial hot filament CVD that allow us to grow on 50 by 50 centimeter area. So devices that we put in the market with ADT, the first one, UNCD coated mechanical pump seals. Most mechanical pump seals in the world are silicon carbide seals with a friction coefficient of 0.5, and they have to be replaced in 4 or 5 years. With the UNCD coating, the people now save up to 20% in the cost of energy of running the pump because of the 0.02 friction coefficient, and they don't wear. So you can have UNCD coated silicon carbide seals on pump for a long time. Then Merck Millipore came to us because they were having problem with the bearings, both from biofouling to produce pharmaceutical drugs. We coated with UNCD, and they have been buying our UNCD coating since 2011 because no biofouling and there is no degradation. The other thing we developed is a Nadia probe, which is an atomic force microscope probe with UNCD coated on the silicon tip. And this probe, you can have it for a long time because it doesn't degrade like the silicon tip when you do AFM. And now what we are working extensively is in developing this water purification system that involves boron top UNCD coating on metals. Our UNCD coating cannot be corroded by any fluid, water, anything, including hydrofluoric acid. So what we demonstrated here is that by passing a current to boron doped UNCD metal electrodes, we can create ozone, and ozone is killing all bacteria, funguses, and everything in water. So this is a process that we may be able to produce water purification in 5 to 10 minutes. And also for cleaning surgical instrument and mobile disinfection and other things. So science and technology of UNCD coated for implantable medical devices. From 2000 to 2010, I was part of a big project involving 5 national laboratories. I was at Argonne National Laboratory at that time, 4 universities with the University of Southern California, Doheny Institute, and a company in California called Second Sight to develop an artificial retina to restore partial vision to people blinded by retinitis pigmentosa. That is, there is a gene that starts killing the photoreceptors in the retina, but it doesn't attack the bipolars and the ganglion cells. And the way you are seeing me is because the photons from your computer gets into your eye, excite the photoreceptor, translate into electronic charges, amplified by the bipolar cells, go into the ganglion cells, and all those charges go through the optical nerve into the brain to form the image. So there are some millions of people worldwide between the ages of 12 to 25 that become blind by retinitis pigmentosa. Once the last cell die in the macula, they become totally blind. So the idea is to have a silicon microchip implanted inside the eye, receiving an image from a CCD camera, producing the image and injecting electrons directly into the ganglion cell to go to the brain. The problem is that when Second Sight with the other people started putting silicon chips in rabbit eyes, they were destroyed in about 10 minutes. So I was giving a talk showing that our UNCD coating cannot be chemically attacked by any fluid. So they brought me into the program, and I developed the UNCD coating to encapsulate the silicon chip. And we are the only ones that can do it because you cannot heat a silicon chip which has about 450, 500 degrees. And we can grow this film at 350 to 400 degrees. So we demonstrated that UNCD coated silicon chips implanted in rabbit eyes, on the top SCM before implantation, on the bottom after implantation for about 3 years. XPS analysis showed total inerness of the UNCD coated silicon chip. We were, our device called Argus 2 was named one of the top 23 inventions in 2013 by Time magazine. So we did 10 years of clinical trial in USA, UK, France, Switzerland, and Mexico, implanting 31 people. Here on the left, you can see a senior man that was blind for 25 years, that with 16 electrodes was able to see those letters, and he was able to recognize devices. So after all these years, we went with Second Sight to FDA in the United States to request approval to implant the Argus 2 device to blind people to retain partial image. They cannot recognize a face, but they can recognize shapes of the bodies, can see doors, windows. 1 year from January 2010 to December, no answer. We got together. I am from Cordoba, Argentina, land so revolutionary. I suggested let's go to Europe because I was talking to friends in Europe. So we went to Europe, got approval in 6 months, and the first Argus 2 device was implanted by Dr. Stanislao Rizzo in his world-class clinic in Pisa, Italy, that returned partial vision to people in Europe. Then we came back and went to FDA and told them that this device was being implanted commercially in Europe, and they approved it in 6 months. So that's why I'm doing now all the other devices. So this is a long video. I'm going to show you very quickly some interesting aspect of the video. So this is of the whole group. And here we are seeing all the electronics, everything that was developed. That is the first device with 16 electrodes, platinum 500 micron on a polymer base. And that is retinitis pigmentosa. And the whole group was directed. The device that is in the market now is with a microchip inserted in a metallic layer outside the eye, connected with platinum wires enveloped in polymer, because FDA hasn't approved UNCD coated silicon chips to put in the eye yet. So this is Mark Humayun at in the center, the surgeon from the Dokinia Institute that directed the program. There are all the people, biologists, mechanical engineers, material science, electronics, you name it. So then here is the argon cream plasma, creating the UNCD coating, encapsulating the silicon chip. And the reason this is so important is because you are going to see there a lady in England with 350 electrodes now. They can do what you can see in here after being blind for 20 years. So this is real. There is the first surgery implanting the 16 electrode device. And we got help from Hollywood to promote in a 1-hour program. That is Alan Alda, a very great actor from Hollywood that puts a lot of money in science and technology. Okay, I don't think we are going to be able to retain full vision with this technology. But what we demonstrated in the last 5 years is that we can grow embryonic, pluripotent embryonic stem cells on the surface of UNCD, and they grow extremely well, better than in any other scaffold. And with electric fields on the nitrogen electrically conductive, we were able to demonstrate that we may be able to differentiate those cells into photoreceptors, as shown here in red. So if we can do that, and the surgeon can implant the photoreceptor in the retina, and they make the connection, maybe. This is science fiction for now. But remember, the trip to the moon was science fiction in 1900, and mankind got there in 69 years only. So the other thing I am doing with my colleagues in Argentina is to develop a process, a UNCD-coded valve, like the Ahmed valve or the Abbott valve, that are used to treat glaucoma. Glaucoma is a condition produced by the clogging of the trabecular tubes in here that drain liquid from the eye continuously to keep the pressure of the eye normal. If that gets clogged, and if you don't drain the liquid, the person becomes blind. So the problem is that these valves are extremely hydrophilic, and in 24 hours, you can get them coated with fibrosis. This is a UNCD-coated Ahmed valve, commercial valve, 1 year, totally clear, because our UNCD can be done extremely super hydrophobic, as I'm going to show in next slides. The other process we developed is a new process to do retina reattachment. Currently, if you get a retina detached, they insert an oil or a gas bubble that puts the retina, laser treatment through the eye, or cryogenic treatment from outside. With this process, you cannot fly in a plane for 1 year. And if it's at the bottom, the rate of success is very low, because the doctor send the patient home, has to be upside down for about 10 days because the gas bubble and the oil bubble goes always up. So what we develop is a new process where we put a UNCD-coated magnet outside the eye, as indicated in here. We inject super paramagnetic nanoparticles that are iron-2, oxygen-3. Fortunately, these particles are approved by FDA in the United States to do other treatment, and they become magnetic only when they see a magnetic field. So what happened here in the laboratory happened on the eye here. The particles are attracted, push the retina. After 10 days, the retina is attached. We take the magnet out, the particles dissolve. Dental implants. Many people need dental implants, and the 90% of the dental implants put in the world today are titanium, 6 aluminum, 4 vanadium. What people didn't pay attention is that when you put titanium or alloy in the eye, in the mouth, already have a titanium oxide layer. What we found about 6-7 years ago when we did the first studies is that titanium oxide particles are dislodged by chemical attack by the oral fluids, and they start killing cells like crazy. They get into the tissue, and we found in the experiments with animals, many of these titanium oxide particles find their way into the bloodstream. Not good. So what we did, 5 years of animal studies with our colleagues in the University of Buenos Aires, Argentina, And we coated the commercial titanium alloys with our UNCD, as shown here on the left. And what we found is that cannot be attacked at all by the oral fluids. And most importantly, the cells from the maxillary bone grow with high uniformity and with much higher density than on the metal. Then we got together with Dr. Lopez Chavez in his bioengineering humana avanzada clinic in Querétaro and did the clinical trials since 2018. Here on the top, you see the first lady, where we put a UNCD coated dental implant next to a commercial titanium alloy dental implant. So after 3 months, the patient came. No pain at all after putting the force. Very good attachment to the bone. And then we did it more quantitative by putting a device that measures the force, una presión de 35 up to 55 newtons, no pain, nothing. So anyway, we have implanted 50 patients in the clinic in Querétaro, Mexico, and we are projecting to try to bring it into the market in Mexico by 25, 26, then go to the next big market in Latin America, Brazil, and Europe, and the two big markets in Asia and the world now, China and India. So we are also working with a surgeon in Dallas that is producing, implanting these hips and knees. And again, all these metal hips and knees have serious problems of corrosion and fatigue and high friction. And with the UNCD coating, we are going to be able to eliminate all those problems as well on these prostheses. So here we see that with oxygen plasma, we can make the UNCD surface totally hydrophilic to do the growth of the cells, but with 5-10 minutes carbon tetrafluoride plasma, we have demonstrated the highest superhydrophobic surface with a contact angle of 178 degrees. Nothing sticks to the surface of the superhydrophobic UNCD. So Robert Jarvie came to us to see if we could coat the valves of the artificial heart with UNCD to avoid the sticking of the blood cells on the hydrophilic surface. We have demonstrated that. We have problem with FDA approval. And now I am collaborating with the cardiosurgeon in Brazil and demonstrated that the UNCD coating of the stent could be the solution to the many problems they have with the metal stents, cobalt, nickel, and chromium alloys. So we demonstrated that we can grow a PCT fin with top and bottom platinum electrode on the UNCD surface. We put a biocell, a biomolecule here that can attract these molecules that are dangerous from animals. And we demonstrated that by applying a 3 volts on between the top and bottom electrode, we can then vibrate. And when the anthrax molecules are attached here, that is the detection for anthrax molecule. The piezoelectric thin films also have the property that if you can move this mechanically, you can get electrical current from the bottom top electrodes. So what we did here, we put a cell of a heart, a mice, and demonstrated that we can get current out, and we are trying to develop this to power defibrillator pacemaker, because the defibrillator pacemaker today, with a graphite on copper electrodes for the batteries, they degrade sooner than desirable. And that's no, because my wife got a defibrillator pacemaker maker from Medtronic in 2013. They told us that in 9 to 10 years, they were going to change the whole box. It was only 6 years. And now we demonstrated that if we coat this graphite with our NUNCD electrically conductive, we can get flat capacitive energy as a function of charge discharge, as opposed to the degradation observed in all these commercial graphite on copper anodes for lithium-ion batteries. So we think that we are going to be able to produce a new generation of implantable medical devices. Also, we are developing electrode for the neural stimulation, and a transformational, multifunctional, low-cost ultra-nanocrystalline diamond, enabling new generation of industrial, high-tech, and implantable medical devices, prosthesis. And the future is that we demonstrated recently that we can grow high-K dielectric nanolaminate of titanium oxide, aluminum oxide on hydrogen-terminated diamond and produce the first CMOS devices based on diamond. And the reason we want to do it on diamond is because diamond is the highest thermal transport material, both perpendicular and in the surface. Graphene is higher in the surface, but perpendicular is too low. So single crystal diamond would be the way to do to really cool the next generation of microelectronic devices. So we think that we will be able to grow the diamond man and woman. This is all in a book that was published in 2022 by Cambridge. And thank you very much for your attention.